Hello, everybody. Can you hear me? So welcome to warm San Diego. I very much appreciate the organizers, especially Mohammed and Christian, for giving me this wonderful opportunity. So as Christian mentioned, my research is on this wearable ultrasound technology. And the first question I have to answer is, why do we need wearables, right? So what you're looking at here is a picture showing a scenario when those patients are connected by many wires. And obviously, those wires are tethering, cumbersome, needs a lot of patients, clinicians' time to connect those wires. And those wires are obviously obtrusive, it limits in the patient's mobility, and also those measurements are only available in the hospitals. When the patients leave the hospitals, the doctors have no idea what's going on, so they miss a lot of information, miss a lot of data. And sometimes when those patients are critically ill, then the doctors will have to order invasive procedures, such as surgery, blood drawing, so on and so forth. The holy grail of this wearable community is to come up with a technology like this. So this device is flexible, stretchable. It can be laminated on the skin without any obtrusive constraint on the patient. So it can provide 24/7 monitoring. It's almost like a secondary electronic skin on the human body. And this device is portable, can provide like a continuous monitoring, does not miss any data, critical moments, especially during those disease transition periods. And also, this device will be able to access the central organs, deep tissues, without breaking the skin. So if you survey the market, survey the literature, you will find out that there are so many wearable devices. Some of you may wear the Apple Watch, a Garmin, a wristband, so on and so forth. These wearable devices are so powerful, functional. They can measure a lot of things from the human body. But if you think about it carefully, the signals they can measure can be basically put into two categories: physical signals and chemical signals. I'm not going to go through the list of those signals they can measure because it's not my focus. Here my focus is the existing wearable devices can only measure signals from the skin surface or shallow tissues, right? However, there are lots of more signals beyond the skin surface, beyond the shallow tissues, in your central vasculatures, musculoskeletons, cartilage and bones, tissue fluids, and most importantly, the visceral organs, your heart, lung, kidney, spleen, GI tract, brain, so on and so forth. And here's my hypothesis. The hypothesis is those signals in the deep tissues have a stronger and faster correlation to the disease status and the progression than those signals on the skin surface. And those deep tissue signals are yet to be captured by those wearable technology. Then the question boils down to, how can you access those deep tissue signals on a wearable platform, non-invasively and continuously, right? So about 3 years ago, my group published a comprehensive review article trying to summarize all possible approaches that can be integrated on the wearable platform and continuously non-invasively monitor those deep tissue signals. There are 6 of those technologies, including biopotential mapping, vibration sensing, reverse anaphoresis, electromagnetic antenna, impedance tomography, and ultrasonography. We compared those 6 technologies in 3 critical metrics: spatial resolution, penetration depth, and temporal resolution. Eventually, find out that our favorite is ultrasound, because ultrasound can provide a very high spatial resolution, a wide range of penetration depths, and also a fast enough temporal resolution so it can capture those dynamic processes in the human tissue. By integrating ultrasound on this wearable platform, it opens up a new sensing dimension for this existing wearable community. And another reason for us to use ultrasound is biocompatible, is non-ionizing radiation, so it has a proven track record in clinics for this biosafety. You can find ultrasound in almost every division in the hospital, so it's so powerful, so functional. We can leverage this powerful technique to do a lot of things. And then that means wearable ultrasound can do this non-invasive and continuous imaging of those central organs. So what you're looking at here is this wearable ultrasound patch that we developed about 7 years ago. And in this device, there are a 10 by 10 array, 100 transducers. Each one of the transducer is like multi-layered to maximize the signal-to-noise ratio. We particularly use this piezoelectric 1-3 composite to transmit and receive ultrasound. And those are the images showing how compliant this device is flexible, stretchable, and it can be twisted. So you can laminate this device on the human body with minimal constraint. So what are the biomedical problems we want to look into? We first thought about those hypertension, because hypertension is the #1 risk factor for cardiovascular diseases, which kill more people than all cancers combined. So this is the image showing that we can monitor the blood pressure in those deep vessels, right, arteries and veins. So particularly in this neck, there is a artery called the carotid artery that provides perfusion to the brain. And this is a mechanism showing the principle ultrasound transducer emit a beam, and this beam will be reflected by this solid liquid solid interface. As you can imagine, when this blood pressure pulse comes in, your vessel will actually dilate, collapsing, dilate, collapsing. Then that means those two peaks will be shifting back and forth. When we monitor this distance between those two peaks, you are measuring the vessel diameter. Through a series of well-established equation and calibration, we can convert vessel diameter to blood pressure. And because we can transmit 5,000 pulses of ultrasound every second in the human body, that means we can measure blood pressure 5,000 times every second. So this is the temporal, high temporal resolution blood pressure waveform, P2-peak blood pressure waveform has lots of detailed information you can extract from those waveforms. So one advantage of this wearable patch is it can achieve intimate, conformal contact with the skin surface, even without gel. So gel is cold, uncomfortable, is evaporating, so you have to reapply the gel once for a while, and it causes those problems for disinfection if you use the device across different subjects. So this is a measurement result showing that with gel, without gel, you can get the similar quality of those blood pressure waveforms. A lot of people ask me, if you need a calibration to convert vessel diameter to blood pressure, how reliable is your calibration? How frequent you have to recalibrate your device, right? So this is the result that we recently published, and you can see that we tracked the calibration for a period of at least 1 year on 4 healthy graduate students. So what we did was, we did the calibration on day 1, and that's the only calibration we did, and compared the ultrasound reading and the cuff reading on a daily basis for the first month, on a weekly basis for the first half a year, and on a monthly basis for the second half a year. As you can see here, the ultrasound reading and the cuff reading match to each other very well. The discrepancies are within the defined FDA thresholds. So this is for the healthy graduate students. How about for patients? So we compared the ultrasound reading and the A-line. This is casters for cardiovascular patients in the ICU. We can see for one patient, we continuously monitor for 12 hours. For the second patient, we continuously monitor for 10 hours. You can see those two modalities, the readings, the temporal series data match to each other very well. Here is the wavelet coherence spectrogram showing the high correspondence with, between each other. You may say, hey, you probably measured 20 or more patients, and you only show 2 patient data here. No, we only measured 4 patients, and we showed all of the 4 patient data in the paper, and all of them show this high correspondence between those 2 measurement modalities. A unique advantage of this wearable blood pressure sensor is it enables monitoring when you are doing those daily activities at home, right? So we tracked these blood pressure changes on 7 subjects when they were doing different kinds of data activities. For example, 13 of them. You can see, as what we expected, those different activities change the blood pressure waveform, the baseline, the heart rate, the morphology, so on and so forth. And we analyzed those different data activities in these 4 quadrant plots. You can see this is ultrasound data, this is the cuff measurements. Ideally, all those data points should fall on this dashed diagonal. In reality, you can see those data points fall within plus minus 5 millimeter mercury. That means those measurements between those 2 modalities are within these FDA-defined regulations. And this is the systolic blood pressure, mean arterial pressure. We can do the same thing for diastolic blood pressure. One unique challenge for this wearable ultrasound device is, imagine if you put this device on the skin of one location, and you want to monitor your target. For example, there's a carotid artery, and you move around. You say, for example, you rotate your head. Your target, this the carotid artery, will actually be shifting. From this this wearable ultrasound patch because of the distance, because of the depth between the target and the wearable patch, right? And only when this target is directly underneath the patch can you get this blood pressure waveform. When this target is drifting away, you only get this tissue interface, this motion artifacts, right? So to solve this problem, we developed this VGG13 customized algorithm. So in this case, we have an array of 32 channels. At any given moment, there's one transducer on top of the target, and this VGG13 machine learning algorithm will be able to analyze all those channels, scan through each one of them, and eventually pick the best channel, give the best result, and automatically put a continuous blood pressure waveform, even during motion. A lot of people say, hey, your patch is great. How do you send power? How do you communicate the data between the patch and this back-end receiver, right? So recently we demonstrated this circuit that is low form factor, low power consumption, and it can be folded. So this patch is wireless and it can transmit those ultrasound data wirelessly to the back-end receiver, and the entire system is low power consumption, so that the some-size battery can power this entire system for about 2 to 3 hours. And obviously, this battery lifetime can be expanded by tuning those duty cycles and pulse repetitive frequencies, so on and so forth. So this is like for A-mode monitoring, right? You only need a single transducer to get this blood pressure waveform. So we also find out that this A-mode signal from a single transducer is so powerful, it contains all information from those deep tissues. For example, we can use A-mode data, those radio frequency data, to capture those muscle group distribution. How does that work? So as you can probably agree with me, your hand gesture, each one of these finger joints and the wrist angle motion is controlled by the muscle group in your forearm, right? And this hand gesture, each hand gesture and each muscle group distribution has this one-to-one correspondence. If you have a single transducer on your forearm and you emit this, this divergent wave, and those divergent waves will get reflected by those tissue-muscle interfaces, and each one of those reflections will be captured by the same transducer again in the form of this radio frequency signal. That means what? That means each data point on this radio frequency signal has contribution from all those this muscle interfaces. That means each one of these radio frequency signal has contributions from those tissue interface, and that also means those radio frequency signal has one-to-one correspondence with this muscle group distribution and one-to-one correspondence to this hand gesture. If you want to build up this one-to-one correspondence between this signal and the hand gesture using analytical equations, that it will probably take forever. It's probably a task, mission impossible. That's where the AI comes in. So there's a postdoc, Xiaoxiang, he developed this neural network that allows us to, build up those, one-to-one correspondence between this radio frequency signal and hand gestures. And this is the data. You can see here, when we fixed all those finger joints still and only bend the middle finger, you can see those radio frequency signal peaks show up and disappear. The signal amplitude grows and decreases as what you expected. We can also do the same thing for the wrist, right? Fix all those fingers the same, but just rotate the wrist. You can expect similar things happening. And by the same token, we can do those finger bending in some index, middle, ring, little fingers, and perform all those wrist motions. This is the correspondence between the ground truth and the prediction that have very, very high matching from each other. So this is a video showing that we can use this single transducer data to infer this hand gesture entirely. As you can see here, this is a single transducer, this is a wired circuit, this is a battery, right? Single transducer collect this forearm muscle group distribution that can wirelessly transmit to control this robotic arm. You can see in this case, a single transducer data is used to control 2 motors simultaneously that can control this robotic arm to do some sophisticated motions. We can do much more. The degrees of freedom is infinity. We can control literally every one of the fingers using this single transducer data. And a lot of people ask me, muscle group activities can be controlled by electromyogram, EMG, right? Electrical activity. What's the advantage of ultrasound? There are 3 advantages. EMG is very unstable because those EMG is electrical activity. Those neuromuscular fiber firing is uncontrollable, right? It's involuntary. You cannot control when this is firing or not. That's why you see this is baseline. This baseline is very noisy, and this is the first advantage. Second, EMG has no spatial resolution because electricity propagates in the human tissue so fast. You cannot use time of flight to find out the location of the source of the signal. Third, EMG has low signal-to-noise ratio. You have to really clenching your fist. You have to really move your finger very hard. Then you can get some very low signal-to-noise ratio signals. You see, this is the EMG signal. Compared to noise, is very a low signal-to-noise ratio, right? In comparison, ultrasound is very stable. If you keep your forearm stable, the ultrasound signal is stable, right? You do not see any fluctuations. And ultrasound has spatial resolution. You can infer the source of the motion using time of flight, using this echo response, and it has a very high signal-to-noise ratio. You only have to move your finger a little bit. Those ultrasound signals will move like crazy, right? So ultrasound is so powerful, and one powerful technique is so-called phase array. I'm sure for this audience, I don't have to preach to the choir to tell you how does it work. So human body is mostly water, and in order to understand how it behaves in the human body, we have to do characterization in the water tank. So this is the ultrasound patch in the water tank on the water surface. Hydrophone is basically an ultrasound sensor that can map the ultrasound intensity in water in 3D, and this is the mapped result. This is where the ultrasound patch is. This is the mapping of this ultrasound beam. You can see we can tightly focus this ultrasound beam and steer this angle. And the focal spot is about a few millimeter by a few millimeter, and this is very well controllable by the frequency, the penetration depth, and the device or structure. So this is the GIF image showing that we can do those phase array focus and steering, and this is a mapping result. This is a simulation showing this correspondence with each other. So that means what? That means we can actively search target tissue of interest. This is very different from those conventional wearables. For an Apple Watch, if you want to measure something on one location, you have to move this device close to that location, right? And if you change your mind, you want to monitor something else, you have to remove that device and relocate this device to this new location, right? So that is the conventional wearable device based on passive sensing. Here, with the wearable ultrasound technology, we can do active searching, scanning for the target. So you don't have to physically relocate those device if you change your mind of interest. So people ask me, well, if you want to do phase array and your wearable patch is flexible, it's on a dynamic, moving surface, how do you know the transducer location elements, right? How do you know those element locations so that you can do accurate beamforming? So that's a great question. It's a grand challenge in the field. There have been about 10 people in the world trying to tackle this challenge. I would say in order to before we find a perfect solution, we find a temporary solution that can detour this problem. So our temporary solution is to use low frequency. So how does that work? So this is the schematics. For this transducer array, when it's on a flat surface, In order to focus on the right here, focus here, the blue bar is the time delay profile. It's delayed, that means this transducer is activated first. This transducer is activated last, right? This is on a flat surface. For the same transducer array, when it is on a curved surface with a curvature radius of 4 centimeters, this much, it's very, very curved. In order to focus at the same location, the yellow bar is the phase aberration correction we have to add on top of the blue bar because of the curvature, right? As you can see here, the yellow bar is very, very small. It's on average less than 5% of this blue bar. That means what? That means we can safely ignore this yellow bar and directly apply this blue bar to the curved transducer array, right? And that is a hypothesis, and here's the experimental results. So for the transducer array, when it's on a planar surface, we applied a certain time delay profile, so it is focused and steered with a steering angle of 15 degrees. For the same transducer array, when it's on a curved surface with a curvature radius of 4 centimeters, we applied exactly the same time delay profile. As you can see here, it was also focused with the exact same steering angle, but slightly reduced intensity. That means what? That means we can treat this curved transducer array on a curved surface as if it's on a planar surface. The reason why we can do this treatment is because we use a low frequency, 2 megahertz. Low frequency has long wavelengths. Long wavelengths is not sensitive to those transducer element dislocations. So with that in mind, we can do a lot of interesting things. For example, Doppler sensing, Doppler imaging, sensing blood flow, right? And people ask me, can you sense blood flow in the brain, behind the bone? And as you can agree with me, bone strongly attenuates, reflects ultrasound. So to overcome this challenge, the student Zhou Sai, he basically learned from the literature this ultra-fast imaging. And if you do not know what it is, it's basically a technique that allows you to transmit and receive hundreds of thousands of pulses every second so that you can do lots of averaging and accumulation so that your signal-to-noise ratio is significantly enhanced. And this is a 3D power Doppler imaging of the blood flow in the brain. You can identify all those major branches in the cerebral blood vessel. And this is a view of the blood vessel in different angles. You can see that for a healthy subject, the left side and the right side are symmetric to each other. And we can also record the blood flow spectrum, and you can see the waveform morphologies are very different, and also the directions are very different, right? So that's what we expected. And we also did some maneuvering, as you can see, for a normal case. As I said, the left side and the right side are symmetric, but if you compress on the left side, use your finger to compress the carotid artery, that means the flow into the brain on the left side is reduced. Automatically, the flow to the right side is enhanced, as indicated by those thicker arrows, right? So you can see the left side, the arrows are thinner, so compared to here, because of reduced flow on the left side. And this automatic adjustment is after millions of years of evolution by the human body, and that's not very surprising. However, what is surprising is that when we use this wearable patch for long-term monitoring, in this case for 4 hours of monitoring continuously in the middle cerebral artery, what we find out is that in the middle of the monitoring, the subject becomes sleepy, becomes drowsy. And we notice this peak systolic velocity had this low frequency oscillation with a frequency of about 0.1 hertz. And this low frequency oscillation is a so-called B wave. Is associated with lymphatic flow in the brain for removing this toxic waste, memory consolidation, so on and so forth. And that's a very, very hot research field in the neuroscience field. And that means our technology can provide evidence, provide data for the fundamental neuroscience community. Ultrasound is a mechanical wave, so it can sense the mechanical properties of the human tissue, such as tissue stiffness. And the student did this phantom experiment by monitoring the stick stiffness when he flies from the bottom in the lab. We can see as time goes by, the bottom part gradually dehydrates. When dehydrates becomes stiffer, right? You can see as time goes by, the bottom part becomes stiffer and the interface grows. How do you know your stiffness mapping is accurate? So this is the 3D mapping result from the wearable patch compared with the 3D mapping result from this magnetic resonance elastography, and this is like a $2 million or maybe $5 million equipment. You can see those mapping results of this human anatomy match to each other very well, and also the numbers, the boundaries are also very close to each other. They have some discrepancy because those two modalities are based on different principles and also radiation frequencies. So ultrasound is most famous for B-mode imaging. And for cardiologists, those are the 4 standard views they use to diagnose your heart, including apical 4-chamber view, apical 2-chamber view, peristernal long axis, peristernal short axis views. So this is the schematic showing the cardiac anatomy. This is the imaging result from the wearable patch, imaging result from the clinical imaging device. You can see the similar quality between them. And what I want you to notice is, if you slide the cross-section along this direction, you can get these different views, so-called the basal view, mid-cat view, and the apical cavity view. And if you superimpose all those views together, you got the so-called 17-segment model, with each segment corresponding to one area in your heart, corresponding to this myocardium, right? If you monitor the beating behavior of each segment, you know which part of your heart muscle is beating abnormally. And this is so-called regional wall motion abnormality. And there have been clinical evidence to show that those regional wall motion abnormality is about half an hour earlier than the conventional EKG to predict heart attack. And as you know, heart attack is very acute. People can pass by within like 1 or 2 hours. So by knowing this half an hour earlier can potentially save lots of lives. And this is the video showing the student is doing this imaging in the lab. As you can see in this wearable patch, there are 2 orthogonal arrays, 2 linear arrays that are perpendicular to each other. And those 2 linear arrays can form 2 B-mode images simultaneously, independently, and in real time. And those are the 2 images. You can identify those interesting cardiac structures and functions. So what I want you to notice is, in this video, when there's a student put his patch on his chest and he started to do some motion, he started to do some exercise, and the image quality, the imaging performance is not compromised at all. That means what? That means we can start to do imaging during motion. And the reason for this is because this patch has intimate conformal contact with the skin, human body, right? So we can start to do those stress echocardiography. And in the hospital right now, they can only do imaging before the exercise and after exercise. I have done this myself in the hospitals. And what is really important is how your heart is behaving during exercise. And the reason for this is because some of those cardiovascular risks will not show up until you put the maximum stress exertion on the cardiovascular system, right? So with our wearable device, we can do those imaging during the entire process, before, during, and after exercise. So this is extracted M-mode images. You can see lots of data. And you think those are noises. If you zoom in, each one of the peaks, each one of these changes corresponding to either heart beating, diaphragm motion, breathing, valve closing, opening, so on and so forth. Lots of interesting features we can extract. So wearable imaging is enabling continuously acquiring those data from the human body, right? If you show all those data to the doctors, to clinicians, they will be overwhelmed. They will ask you, what are the actionable information, right? So to save their burden, we developed this AI algorithm based on FCN32. In this case, we can extract this left ventricle volume from this apical 4-chamber. And from this left ventricle volume, we can derive stroke volume, cardiac output, and the ejection fraction. And this is the data, left ventricle volume data, lots of information. If you zoom in those 3 critical moments, you can see that this left ventricle volume is very, very triangular, and the heart rate is very fast. And after a few minutes, you can see this left ventricle volume waveform morphology is different. It starts to show this diachronic notch, and heart rate is slower. From this left ventricle volume waveform, you can derive ejection fraction, stroke volume, cardiac output, and heart rate. You know what, guys? Hey, everybody. I know it's already a long day already, right? If you look at those waveforms, they are no different from any other waveforms you see in the paper or in presentations, right? That's for you. But for me, they're so valuable, they're so exciting. You know why? In the hospital right now, they can only measure those numbers using invasive procedures, such as Swan-Ganz catheter based on thermal dilution. And they can only measure only one number per 1 second or 2 seconds. So it's very low temporal resolution. Here, we can measure 30 numbers every second, and this is totally non-invasive, right? So that can bring lots of value to the clinical community. I'm really counting on this technology to become famous and rich. So ultrasound is physical wave. It can measure blood pressure, measure blood flow, measure the tissue stiffness, and form those B-mode images, right? How about the chemical information? There are lots of chemical molecules, reactions in the human body, in the deep tissue. How can you extract those chemical information, right? So this is done by those photoacoustics imaging. And for this audience, I don't think I have to preach to the choir, but basically, this is the imaging result. We use those 850 nanometer laser to differentiate blood from those other 4 healthy liquids: fat, water, and milk plasma. This is the B-mode imaging, and you cannot really tell them apart, but with the photoacoustics, you can tell the blood apart. If you find those liquid in the human breast cyst is healthy, but if you find the blood, it's like a strong biomarker for the breast cancer. And this technology empowers the patients to do more frequent monitoring and screening at home, encouraging early discovery and better the treatment outcomes. And the photoacoustic signals are proportional to this core body temperature. And this is a 3D mapping result. In the phantom, you can see the warm region, cold region, somewhere in the middle is a gradient. And this is the mapping result. After a few seconds, you can see that it becomes more uniform. We inserted 2 thermocouples. You can see the thermocouple reading and the photoacoustic reading match to each other very well. So people ask me, well, so ultrasound is so mature, right? And what are your value-added benefits to the ultrasound community? I would say it's so powerful, functional, but it still has 3 critical limitations. First, it has to be manually applied, requires the experienced user. And this creates a problem for so-called operator dependency. This is a grand challenge for the ultrasound community. And because it requires an experienced user, so this measurement is very expensive. And this measurement is only normally done in the hospital, is one-time testing, and it creates only a snapshot of what's going on, and the patient has to remain stationary. It cannot move around, and this requires gel. So with the wearable patch, it's hands-free. You just have to slap it on any part of the body you want to monitor in. You can do those electronic scanning, 3D volumetric imaging, AI-based data interpretation. It empowers the general user to use it, right? So it's operating independent, it's low cost, and this is continuous. You can do it anywhere, anytime. It provides comprehensive data, and it can do monitoring during motion, so you can couple stress during this examination process, and this is gel-free. So with that, I want to conclude by acknowledging my students and the postdocs. I'm learning from them every day, and also my critical collaborators, and also those funding support from those federal agencies. The size of the logo is roughly proportional to the amount of funding I accumulated over the years. Thank you so much.